Kia ora koutou. My name is Kerry Parker. I'm a teacher at New Plymouth Boys, and I'm trying to work out how to develop some really good hands-on activities for teaching about heat and energy, especially for the new level 1 curriculum. And what I'm doing here is I'm using a cheap jug kettle from the warehouse and a cheap weighing scales, digital weighing scales, but you could be using any weighing scales you've got in school. The advantage of these ones is that if there's a bit of a spill, it's not a big deal. There's just a little battery inside of them. These cost about $30 and the jug kettle was about $11. I've got a temperature measuring multimeter here. You don't really need it because what we're going to be doing is measuring the latent heat, the heat of vaporisation of water from the kettle. And all we need to do is to have the kettle turned on so it gets up to a boil, and we need to measure the power that is being turned into thermal energy in the kettle from the electrical energy coming in. So we're looking at the power. Now the kettle has got a power rating on the bottom of it, but I've also got one of these little gizmos which plugs in to the same socket, which is telling me that this is currently taking 2060 watts. It'll be about 2000 watts. And what I've got to do with this is I've got to get the kettle completely boiling. And now I have to keep the lid open because then I'm sure that it's not going to just keep turning off automatically. And now what I'm going to do, now it's thoroughly boiling, is to zero this and start my stopwatch at the same time, which is very difficult. So start the stopwatch, zero the scale, and I'm going to let it keep boiling. And so this scale now is reading more and more negative as water is leaving the kettle. So I'm going to give it about a minute. And we'll see how much change in mass there has been in a minute. Taking, according to this, 2060 watts. So the power is 2060. The temperature's flickering at about 101. And the minute is up. And it's reading. Now the scale has been jumping around because the kettle's wobbling, but it's become steady almost immediately that I stopped the boil. And it's down at minus 55, minus 56 grams. So it lost 56 grams of water in 1 minute with a power of 2060 watts. 2000 would have been close enough. Kia ora. I'm just going to show you how to do the calculations for that experiment. So we had a power from the kettle of 2060 watts. I measured that with the special little machine I got from JCar, but you could just read it off the bottom of the kettle if you didn't have one of those. And we timed it for 1 minute. And of course, we're going to remember to turn it into SI units, so that's 60 seconds. And the change in mass that we measured was 56 grams, which of course is 0.056 kilograms. So the energy that we used, work that out as power times time. So that's 2060 times 60 seconds. Which comes out as 600 joules. And what we know is that the change in energy, the energy that went in to evaporating the water, gave us the change in mass times that heat of vaporization. So L equals delta E over delta M, which was 123,600 divided by 0.056. And that was joules, and that was kilograms. And that works out to being 2207 times 10 to the 3. I'm falling off the edge of my paper. Times 10 to the 3 joules per kilogram. So we could call that 2207 kilojoules per kilogram, which is how the numbers often reported in the literature. And I looked it up on Wikipedia, and the value that they have from Wikipedia was 2257 kilojoules per kilogram, which is pretty darn close. I think I was probably a bit lucky this time. I've done it other times and got slightly different numbers, but it's always in the 2000s and so's, and it's a pretty good, simple, quick demonstration of how to measure heat of vaporization.